When the force apply at the node directly, you can put this inside QK, right? If the force or moment apply at the node directly, you can put it inside QK. But what about this intermediate loading? In this section, we would like to derive the equation, modify the equation a little bit to handle intermediate loading. So here, you can see that in the past, we derived our equations for load applied at the end of members. But quite often, especially for beam mainly used to take uniformly distributed load, maybe from the slab, or maybe from the other scenario, the other properties, the other events. So what happens if we have UDL or loading at the middle? We would like to derive the formula again using this principle. This is, I think, is the fourth time, right? Using these terms, principle of superpositions. We keep applying using this principle to derive our formula. But bear in mind that there is some assumption for this principle of superpositions. This principle only valid for structures with small deformation, linear elastic. Otherwise, you can't apply principle of superpositions. As soon as that the material remains linear elastic, deformation is small, then you can use it to derive our equations. How? I show you the outcome directly. Actually, you have learned slope diffraction formula. This is the slope diffraction formula you learned in the other fundamental analysis module. Moment equal to a set of rotation diffraction plus an item called fixed end moment, right? When you learn the slope diffraction equations. This fixed end moment actually is used to take account of the intermediate loading. So mathematically, it's just like adding one fixed end force vector on the right-hand side of the equation. The formulation is quite similar to the one that we encountered last time for truss structures under temperature change or fabrication error. If you have this kind of additional effect, you have to add one additional vector on the right-hand side. To make things consistent, I call this Q0 here. Okay, I think last time in chapter 1, we also call this Q0, something like that. They are used to take account of this kind of extra effect, like intermediate loading. Then how to calculate their values? How to calculate the values of Q0? This is the equation that we keep using. Q equal to KD plus Q0. Q can be decomposed into QK, dk. QK is used to describe the force applied exactly at the node. dk used to describe the support displacement. Normally 0, but sometimes non-zero, just like our example 2 before. Q0. Q0 is used to take account of the fixed end moment. How to calculate fixed end moment? Well, there are some formula. I extracted from the textbook. Normally, if you have textbook, you go to the first page or go to the back side of the textbook, back cover. Then there are a lot of tables show you the fixed end moment or some standard formulas. Here I just consider 2 classical examples. These are the 2 cases that I will assess you in the quiz or examinations. But when you read the textbook, there will be more. But to control our scope of this module, here are the 2 scenarios that I will assess you. Firstly, a beam under UDL. If you consider a UDL between 2 nodes, then the fixed end force, fixed end moment can be calculated using this picture. The force equal to WL over 2, while the moment, the fixed end moment, equal to WL squared over 12. You can arrange them in a vector form because, in Sylvus method, we always arrange our components in a vector or matrix form. Ny, Nz, Fy, Fz. Here is N, here is F, as usual. For UDL, you can find out the Q log vector, Q0 vector using these expressions. And then for if there is a force applied at midspan, a concentrated force at midspan. This is the near end node. This is the far end node. If the concentrated force is not acting exactly at the node, but in between the 2 nodes, then you can also handle the problem using fixed end moment. The force and moment are shown on this picture. So every time when you need to handle intermediate loading, you can go back to this picture this line, page 46. Find out the corresponding fixed end force, fixed end moment, according to the nature of the force, and then put it back to this equation. So Q0 is not unknown. In the other words, Q0 is well defined, depends on the loading. You know it at the beginning. Depends on the nature of the loadings. So here you can see that you know QK, you know DK, you know Q0. K is something that you know. You can construct a matrix yourself. So go back to the original problems. Your task is to solve for DU and then QU. A very, very systematic approach. Then how to derive the problem? How to derive these equations? I show you a few steps. I'm not testing you derive, so here I turn this to reference. I just asked you how to apply the equations, how to find out Q0 and solve it. But when you derive the if you want to derive the equations, you can use superpositions. What is superpositions? Superpositions mean you break down a complex problem to a different simple scenario, and then add up the outcomes together. So here, scenario 1, case A. Case A, we apply assumed loading directly acting at the nodes. The values the magnitude is equal to the fixed end force of fixed end moment, as I showed you before, but the direction difference. This scenario, there is no loading at the middles. Scenario B, we consider our fixed end force, fixed end boundary conditions. Fixed end here, fixed end here. And then there are fixed end force, fixed end moment on the two sides of the problems. So when you add up these two scenarios together, add mean addition. When you add up these two scenarios together, you can see that the force on the two nodes cancel out. Only the UDL remains at the middle. So it can simulate the actual problems. UDL scenario. Equation will be the one that I showed you before. Here you can turn this to 0. F means fixed end moment, but to make the symbol consistent, you may call the second terms on the right-hand side as Q0. So actually, this equation comes from superpositions. Break down complex problem to two simple cases, and then combine them together. But more important is to understand how to use this equation to solve our beam problems. How to use it? There's one example to illustrate how we can use these equations. Here, example 3. Example 3, determine the moment developed as support A. Here is support A, that means the fixed end. The moment at fixed end. I think I also asked you to draw the shear force and moment diagram, although I did not raise the questions right here, because I want to show you more information, right? Not just stop at moment, but you can proceed to the moment and shear force diagrams. So have a look at these problems. We have one fixed end on the left-hand side. We have two roller support, one at here, one is here, one is on the right side. The first span of the beam is under UDL. The value is 32 kilonewton per meter. Well, on the second span, there is a concentrated force acting at the middle of the second span. The value is 48 kilonewton. Okay, so we also give you E and I. You know E, you know I, you know EI. So you can find out the numerical value exactly. There is no symbol in the answer. So how to deal with this problem? Different people may have different discretization skills. The procedure is quite systematic. You firstly conduct discretization, a cycle number, and then find out element matrix, formulate the force displacement equation, and then solve it. The procedures are always the same. But the problem is, hey, how to discretize these structures? To discretize these structures, there are two ways. Method 1. Some guy may like to divide the problem in this way. Element 1. Oh. Element 2. Element 3. Some guy may like to divide the structure into 3 elements. 1, 2, 3, 4. There will be 4 nodes. 3 elements. Well, this is one option. You can cut into this manner if you like. But in this problem, I would like to use more easy way. Instead of dividing these structures into 3 elements, here, I would like to divide these structures into only 2 elements. Element 1, element 2. I cut these structures into only 2 elements. Then what is the consequence? If you divide these structures into 2 elements, 1 and 2, 3 nodes. If you divide these structures into 2 elements, 3 nodes, then you can see that UDL is intermediate loading, right, in between 2 nodes. 48 kilonewton, this concentrated force is also applied in between 2 nodes. So this time both applied loadings are classified as intermediate loading. We have to convert them to fixed end force vector, Q0, and then put it into our force displacement relationship. Okay, here we use fixed end moment, the concept, the picture that I showed you before, to handle this problem. We have 2 intermediate loadings because they are applied in between the 2 nodes. Element 1, element 2, each node we have 2 degrees of freedom, 1 vertical, 1 anti-clockwise. So we have totally 6 arrows. 6 arrows mean we have 6 degrees of freedom. 6 degrees of freedom, we have a structure sequence matrix equal to 6 by 6. The structure sequence matrix is 6 by 6. You can determine the size of big K immediately. And then second, assign the code number 1, 2, 3, 4, 5, 6. I think I'm also using the textbook method in this example. The textbook method means you have to identify where you have unknown displacement, where you have known displacement. We can consider each node separately. Say, for example, we start from the right, we start from the left and then go to the right. The left end is a fixed end. Fixed end is a very nice support because as fixed end, normally you have no movement, no rotation at fixed end. That's why we call it fixed, no movement normally. 0, 0. At roller support, roller support at node 2, at roller support we have no vertical movement because the structures cannot go inside the ground, right? No vertical movement, but it's free to rotate. Free to rotate at roller support. And then at node 3 is another roller support. The nature is basically the same as the node 2. No vertical movement, and then the rotational degrees of freedom is question mark, unknown rotations. So when you take a look on this picture, we have 2 question marks. That means you have 2 unconstrained degrees of freedom. You have 2 unknown displacement, simply speaking. You have 2 unknown displacement. Then what is the size of K11? If unknown displacement is 2, then K11 is a 2 by 2 matrix. It's relatively easy to solve in these problems, although it's not complicated. And then you can assign code number. You can assign code number starting from the position with question marks. Let me have a look. My assignment. Assign the code number starting from the right-hand side here, 1 and 2. 1 and 2 are used to describe the positions with unknown displacements. And then you can assign the remaining 4 numbers arbitrarily. 3, 4, 5, 6. This is the code number diagram I would like to use in this example 3. When you work out this example yourself at home, you may reconstruct the code number diagrams to practice the skills. You should get the same answer if you follow the step properly. And then you can assign and you can set up the known force, known displacement vector, dkqk. You know it's dk, right? dk is the zero displacement. dk is the known displacement vector, which means the support displacement. All 0 in this scenario, relatively easy. All 0. D3, D4, D5, D6 are 0. We just analyze together, right? We have 4 0 at fixed end, at raw support, at the middle and on the right. The corresponding code number is 3456 DK. If you use the shortcut, then QK, you know the size, you know the code number, right? QK involve code number 1, code number 2. You know the code number for QK, but what about their values? Well, their values is equal to 0 here because we do not have any applied moment. We do not have applied moment on the pictures. On the pictures, you cannot see any applied moment. There is no applied moment at these two positions. That's why if you follow our notation, QK becomes 0. 0, 0 correspond to node 1 and node 2, direction 1 and direction 2. Then you may ask, hey, where about the fixed end force? Where about the concentrated force? And what about the UDL? We will put them into the Q log vector, the second term in our matrix equations, the fixed end force, right? Fixed end force and fixed end moment. We convert them to the fixed end force and fixed end moment. How to do so? On the next page, I will show you how to do the conversions. But here, you can see QK and DK. They form part of our force displacement equation relationship. But this is our final target. We know part of Q, we know part of D, we know this is what we have at this stage. We will try to put all the things into the equation before solving it. How to find out the fixed end force and fixed end moment? I consider element 1 first. Here is element 1. Element 1. You can go back to the previous, the page with fixed end force diagrams. I forgot the page number. You may go back to the previous sections. I copy the picture on the top right-hand corner. From the picture, you can see the value of the fixed end force. The force is WL/2 here. W is 32. The length is 6 meters long for element 1, and then divided by 2. You can find out the force and moment. Did I show you the force? The force here. The force is equal to 32 times 6. 6 is the length of element 1 divided by 2. So the force, 96 kilonewton. The fixed end moment, WL²/12. The value is also equal to 96. Fortunately, same numbers, same relative, but they have different units. For force, we use kilonewton. For moment, we use kilonewton meter. Be careful of the unit. Wrong units, you get a totally different answer. So we have fixed end force. Convert this picture in a vector form. Convert this to a vector form. For element 1, I put a superscript on the top to denote that it is element 1. The value is equal to 96, 96, 96, and minus 96. What are they? The first element used to contain the value along degrees of freedom ny, and then nz, fy, and then fz. We arrange our code number in this manner, consistent to our Sybas matrix. What is n? What is ny? This is element 1. Element 1 point from the left to the right. So the left end is so-called, oh, I put down the wrong symbol. The left end is so-called the node n, and the right end is node f. Okay. Then what is the code number correspond to ny? Here, the vertical code number. ny, nz, and then fy, fz. Go back to the code number diagram. This is ny for element 1, nz for here, also for element 1, ny, nz. The code number order is 4352. 4352. The order of the code number for element 1. 4352. Consistent to what we put down here. 4352. ny, nz, fy, fz. These are the code number order we would like to use in element level, starting from log n and then log f. This is the first observations we have. And second, you can see a very interesting thing. The last number is minus negative numbers. minus 96. All magnitude are 96, but the last one is negative. Why? The last one stands for the fixed end moment on the right-hand side of element 1. From the picture, you can see that this fixed end moment is a clockwise moment. Clockwise means negative, according to our sign convention in Siebert's method. Because this one is a clockwise moment. Clockwise, we give it a negative sign. While the other, force, vertical, upward, the moment on the left, anti-clockwise. So they are positive. Okay, be careful about the sign. Otherwise, your whole calculation becomes totally different. You will get a wrong answer if you change, if you misunderstand the sign, the symbol. So this is the fixed end moment, fixed end force vector. Fixed end force vector for element 1. For element 2, you just repeat the same things again. For element 2, you use another fixed end force diagram. We have another one for force at the middle, and then reproduce the fixed end force vector again for element 2. The next line shows you element 2. Here is element 2, and you can see that element 2 is under one concentrated force at the middle. So you can use the fixed end force diagram on the top right-hand corner. Find out the fixed end force, fixed end moment, and then put it at appropriate positions according to your code number. We have also fixed end force and fixed end moment. Here, the force, and here is the moment. Here's the force, and then convert this to our fixed end force vector. Again, we start from Ny, Nz, and then Fy, Fz. Start from shear. The shear is 24, and then moment, 12. And then force again, 24, and then moment. The moment on the right-hand side is clockwise. Clockwise means negative. So you can see that the last element normally negative, because according to the fixed end force diagram, the moment on the right is clockwise, so it's normally negative. The code number order is 5261, 5261. Ny, Nz, Fy, Fz. Next, we have to combine Q1, Q2 together to form the entire Q0 vector. How to combine them together? Just add up the values if they have the same code number. You can adjust, you can enlarge or rearrange Q1, Q2 so that their code number is arranged in ascending order 1 to 6. Fill 0 for those missing elements. Say for example, element 1 involve code number 2, 3, 4, 5. No code number 1, 6. You can fill them with 0 so that the file size is equal to a 6x1 vector. It makes you more easy to observe which part should be combined to each other. Or if you're good in mapping, actually you can map directly from the previous page. But here I firstly enlarge the element and then rearrange the order so that you can see which parts should be imposed with each other. And this becomes the Q0 vector we use in our calculations. Put it on the right-hand side of the force displacement relationship. So we know part of Q, we know part of D, right? We have QK, we have DK. After this line, we know Q0. It seems that the only missing thing is K. If you know Siebert's matrix, then you successfully formulate this equation and then you can solve it. How to find out K? To find out K, we have to use our classical procedures. Find out K1, K2, and then put them together. K1, K2. This time, unfortunately, member 1, member 2 have different length. Member 1, 6 meters. Member 2, 2 meters long. So when you calculate the values, they will have different magnitude inside the Siebert's matrix. So this time you have no choice. We have to calculate all the things right here. But I remember that there are some skills you may speed up the calculation, right? Siebert's matrix is symmetrical, so you can use the symmetrical property to speed up your calculation a little bit. And then you can find out some common terms in the Siebert's matrix. Say for example, you normally see 12 EI over L cubed, you see 6 EI over L squared, and then you also see 4 EI over L. If I did not make any mistake, there is also one term, 4 EI over L in the matrix. Then you can firstly calculate these few common terms. It may speed up a little bit for you to construct the element sequence matrix, put it according to the positions. You can refer to the element matrix. I think I forget the slide number. It should be in section 2, something like this. After that, you can combine them together to form the structure sequence to form the four displacement relationship Q equal to KD plus Q0 plus Q0. Your task is to find out D1, D2, unknown displacement, and then unknown reactions as usual. This is the formula we use in this problem. One thing, mathematically, you can move Q0 to the left-hand side of this equation. Mathematically, you can move it from left to right. Then it will become like this. It will become like this, just like our typical format. When you read the textbook, they start from here. I remember that. But actually, it just moves the fixed and force vector to the left-hand side. They're equivalent. Depends on how you understand the problems. I think this one is more easy because you can construct fixed and force vector directly from the picture that I gave you before. But anyway, our task is to solve the equation, solve for D1, D2 using the first two equations. You can see Q1. Q1 is a 2 by 2 matrix. You can use matrix inverse or you can solve for two simultaneous equations. Here it seems that I'm solving two simultaneous equations. Find out the unknown D1, D2. Their rotation, we use radian for the rotations. Once you have the rotations, you can use it to find out our unknown reactions. If you know the unknown reactions, you can go back to this formula. Once you know D1, D2, you can calculate Q3, Q4, Q5, Q6 by using the bottom part of this matrix equation. K1, this is K21, right? K21 times du is here, plus K22 times dk. But dk is 0 again. Here, dk is 0. So actually, K22 is useless in this problem. It will not affect your calculation because it's multiplied by a 0 displacement, dk. Plus, don't forget, there is one extra columns on the right-hand side, plus the fixed and force. Don't miss this part, okay? Otherwise, your answer will be different a lot. Remember, there is one extra terms on the right-hand side. You can read directly from the matrix equations. And then you can do this 4 times, find out Q3, Q4, Q5, Q6. Then you can get all the reactions. If you know the reactions, you can draw the shear and moment diagrams as usual. Shear and moment diagrams. Please note that you have to understand how to play with the whole procedures, how to do Sylvus method. You have to familiar with the procedures, and then solve it step by step. Find out reaction, find out unknown displacement, and then find out reactions. And then you can use the reactions here to draw the diagrams. Okay. Again, I showed you how to use the member end force equation, but it is optional. If you want to know the member end force, you can turn this to, and you can use method of equilibrium. You can use equilibrium, use method of section to find out any member end force yourself. No need to use these equations. So summary, for these sections, we handle a problem with intermediate loadings. We handle the problem with intermediate loading. So this is the end of this topic. So we finished the second chapter, the second topic, BIM analysis. After the break, we will move on to our tutorial sections. But I will also talk about the lab first, and then we will move on to tutorial sections. But at this moment, we may have a short break for 5 minutes. Testing. Okay, let's continue our sections. Before the break, we finished all the contents in our second topic. Second topic is about beam analysis using CBUS method. So right now we were going to have tutorial sections. I have uploaded the notes on Moodle. But before that, I would like to talk about the lab arrangement. According to the schedule, we will have a lab on the coming Wednesday, 28th of September. About the lab, firstly, you may have a look on Moodle. The Moodle lab sections upload the lab menu, the lab schedule, and also the group list on Moodle. You may have a look. I just received 1 or 2 group lists from up to now. So basically, I form group for almost the entire class. You can find out your group list right here. Group tag. Here. Oh, yes. And this is the group list version 1 I updated yesterday. You can find out your group list. There are totally 7 groups. For the lab sections, you just need to attend the time slot assigned to your group. Say, for example, for group 1, I put down the schedule on Moodle. For group 1, you can attend the section at 2 o'clock. And then for group 2, 4:20, and so on. You just need to attend your own sections, no need to attend all. The lab is extremely simple. Just measure the reactions. Group 1, group 2, group 3, and so on. The lab is quite simple. What we are going to do in the lab, maybe I'll introduce the lab a little bit. The lab sections, we are going to conduct a very simple 2 beam test. This is the lab menu. You can also download from Moodle. This is the lab menu. We were talking about beam test. We consider a simple beam 2-span beam right here. One end fixed and then roller support. Your task is to assign the loading at location indicated by the red arrows. The loading is shown on the previous table. You apply loading step by step for 5, 7, 10, blah, blah. And then your task is to measure the reactions at the 2 roller supports, B and C. Measure the reactions for each loading case. This becomes the lab data reactions. And then based on our discussion before the break, we can use CBUS method to find out the unknown reactions, QU. Right? The target of the lab is just used to verify the effectiveness of CBUS method. You compare the value to see whether they are the same or they are different. This is the target of this lab. So normally the student take around 10 to 15 minutes to complete the test based on the previous experience. So for my opinions, each group has around 6 students each group. But I think you can send around 2 to 3 students to join the lab sections. I think that's sufficient enough to take the data. If the whole group join together, I think it's okay. If all members come together, it's okay. But if some of them are not available or due to the other reasons cannot attend the lab sections, you may send 3 students, I think at least, for each group. And then me and lab tech will also help to arrange the lab. So we should have enough manpower if you send 3 students for each section. Okay. When you submit the report, please make sure that you put down clearly your group members and their contribution, their workload in the lab report. Normally, we allow students to submit their lab report in the last week. I forgot about the week number. Last week, I think it's week 15, right? Week 14 or week 15. I can't remember the exact number. Anyway, the last week, you can submit the report in the last week of this semester. Don't worry, the last week. Please make sure that you put down the name list and workload clearly, because I give you marks according to the lab list on your lab report. Okay, I'm not referred to my group list. Okay, I refer to the report that you submit to me, because normally there are some free rider. Right? I'm a reasonable killer. I will kill the free rider if you do nothing in the lab report. So these are my some announcement about the lab. We will have a lab on the coming Wednesday. You may follow the schedule as shown on Moodle. Wednesday 28. And then I also noticed that we will have a computer workshop on the coming Thursday, 29, right? 29 of September. 9月29號星期四 we will have a computer workshop. I think the time slot is on the evening. We are going to have our workshop on the coming Thursday. If the workshop is about, I did not upload the notes for workshop. I will upload today about the notes for our computer workshops. The computer workshop basically talk about SAP 2000. SAP 2000. I'll upload this one today. Okay, I'm reviewing the notes at this stage. SAP 2000 is a very it's a common structural software in practice in Hong Kong. In Hong Kong, we use SAP 2000. We use ETABS frequently for structure analysis, for topic analysis. The workshop we will talk about the basic operations of SAP 2000. Workshop 1, we consider relatively simple structures. And then just introduce what is SAP 2000, how to use it, how to assign element, how to assign material property, how to assign loading, etc. The first workshop basically focus on basic operations. The second workshop on, I think the second workshop is on week 8, right? Week 8, we will talk about top building and some skills, etc. By the way, next Wednesday, we have lab. Next Thursday, we have computer workshop. These are something you have to have some idea. I think you can see your schedule clearly on your timetable. I just remind you here. Okay. Any questions? Anything you want me to clarify regarding to the lab or regarding to the workshops? The lab is face-to-face. Okay, the lab is face-to-face. There's no online version for lab. About the workshop, you may also come back to school. We will have our workshop, SAP 2000 workshop, on the coming Thursday evening in our computer room. 咁下個星期四啦，咁我哋10樓有個 computer workshop SAP 2000 10樓電腦室嗰度，咁都係 face to face 嘅。Okay, we will build our model together during the computer workshop sections. Okay, I will upload. In fact, I have prepared a SAP 2000 video. I will upload later. But during the workshop sections, I will not take the video recording because it's not preferred to do so. Any questions? Is everything clear? Okay, so far so good. But anyway, I will emphasize again after the second break. Why don't we start our discussion about tutorial 2? Tutorial 2. Tutorial 2, we are going to practice how to use Sylvus method to analyze beam structures. There are two objectives. Firstly, we would like to use Sylvus method to analyze beam under concentrated load, under intermediate loadings. And then we would like to discuss a little bit about the effect of discretizations. We will know what are they very soon. Tutorial example 1. This one is a classical problems. Not classical. This one is a problem 1 to show you one special support conditions. Slider. After now, we normally consider 3 supports. There are roller support, pin support, and fixed end. These are the 3 supports we normally consider up to now for truss structures, for beam structures. But in this example, example 1, you can see that we have one special support on the left-hand side. We call that slider support. This is not roller support. This is not roller support. Not roller. This is slider support. For roller support, we normally put down the symbol in this way for roller support. Or I just put down a ball normally for roller support. Okay. This one is definitely different. It's a slider. Then what is the difference between slider support and roller support? There's one important difference. For roller support, it is free to rotate. Normally, for roller support, right? There's free rotation at classical normal roller support. What about slider? A slider does not allow any rotation occurred at the slider support. So when this structure deform, it will deform in a manner something like this. The angle remains 90 degrees after bending. Before bending, 90 degrees, after bending, 90 degrees. This is the one difference between slider and normal roller support. In this example, I want to demonstrate how to play with this this slider support. In fact, we mentioned this slider support at the beginning during our introduction sections, if you still remember, in our first lecture. You may go back to the first lecture, introduction. We talked about different boundary conditions at that time. But anyway, here is the property. Slider support. There is no rotation at this point. If there is no rotation, that means there should have reactions. There should have reactions, bending moment here, to balance, to restrain the movement of these structures. In this problem, we are going to determine the diffractions at the slider support and also find out the reactions of the beam. Two things, displacement and reactions as usual. And then I will also go one step further through the shear diagram, moment diagram, so that you may practice yourself if you have time. So how to solve this problem? Maybe I give you 1 minute to you may think about the solution procedures. At least you can try to assign the lumbar diagram yourself. Okay, I give you 1 minute. Hesley. So go back to these pictures. If you want to handle this problem using the Sibas method, then you have to firstly discretize the structures into different elements and then assign the code number. At the beginning, I will demonstrate using two elements to solve this problem. Approach run. Approach run, we would like to divide the whole structures into two elements and then solve it. And then I will show you what happens if we change this discretization scheme. That is version 2, approach 2. I will show you later. Version 1, using two elements. Well, when we divide the whole structures into two equal elements with length equal to 2 meters for each element, then you can see that the concentrated load, the point load, is exactly applied on the middle node. It is a nodal force. If you divide the structures into two elements, our applied loading, P, will be exactly acting at the node, at the middle. Then it is classified as nodal force, not intermediate loading. Okay, because the force is applied exactly on the node. So it is classified as nodal force, not intermediate loading. And what is the consequence? The consequence is that when you formulate the force displacement equation, we will find that P should be appeared inside QK. And then we do not have any fixed end force vector for this problem. No Q0. If you do the problem in this way, then we do not have any fixed end force because we don't have intermediate loading. Second, assign the code number. Code number 1, code number 2, code number 3. Why we start from these 3 positions? Actually, we start from, we follow our hashbook method right here. I do this manually to show you what happened. 3 nodes, 6 degrees of freedom. For each node, we have 1 vertical, 1 rotational degrees of freedom. And then according to the hashbook suggestions, you can start to assign code number from a position with unknown displacement first. Where we have unknown displacements, we may take a look on the right-hand side. Right-hand side is ideal fixed end boundary conditions. This one is easy. At fixed end, we have no vertical movement, no rotations. So all displacement at fixed end are well defined. At the middle, it is a free node, no support at the middle. Free node is also easy, I think, because everything are knowns. All question marks at the middle. Then the more difficult node, I think, is on the left-hand side, slider support. Slider support allow 3 vertical movement. It can go up or go down, depends on the loading. So the vertical movement is unknown as slider. But what about rotations? Rotation, as I introduced at the beginning, slider support prevent rotation occurred. Slider support prevent rotation occurred. Different from pin support, different from roller support. Slider prevent rotations. So the rotation at slider is equal to 0. That's why when you assign code number following the hashbook suggestions, you can start to assign code number starting from question marks, maybe 1, 2, 3, and then 4, 5, 6 assign the other positions. This is why we have the following code number diagrams. 1, 2, 3 correspond to the position with unknown displacements, and then 4, 5, 6 represent 0 displacement positions. The following part is pretty straightforward. Just follow our step 2, step 3, step 4. Find out element matrix, put them together, and then solve it. Normally, I think step 1 you have to think about a little bit. Step 1 means discretization, assign code number. This step normally you have to think about, right? You have to think about how to arrange the code number, how many elements you will consider, and yeah, something like that. At the same time, you can take a look of these 4 displacement relationship. We have a force vector on the left, we have displacement vector on the right. At the middle, we have a stiffness matrix, something that we will determine in the second step. At the same time, you can substitute the known information into this equation. We call it QK and DK. Based on our previous discussions, D4, D5, D6, it is called DK, right? DK is 0 because we have no rotation at slider, we have no displacement, no rotation at fixed end. That's why D4, D5, D6 are 0. If you follow the hashbook method to assign code number, actually you know where you have known displacement. I think this is also one advantage of using the hashbook method. You know DK immediately. If you know DK, it helps you to evaluate QK. What is QK? QK is the known force. The shortcut is that if you find that DK involves code number 4, 5, 6, then QK should involve the remaining code numbers. So you immediately understand the size of QK. There are Q1, Q2, Q3. Then you can go back to the code number to see if there is any forces or moments applied along these 3 directions, 1, 2, 3. 1. Direction 1, you can see clearly that we have 1 applied loading, P, along direction 1 in downward directions. Downward means negative. Downwards mean negative. So Q1, minus P, minus P. Q2. Q2 is talking about the rotational directions. So it actually means the applied moment Is there an applied moment along these directions? From the picture, there is no applied moment along these directions. Otherwise, you will see a red arrows on the pictures. But in this case, we do not have any applied moment along direction 2. So Q2, 0. Q3. Q3 means the nodal force along direction 3. Direction 3 is here. Is there any force, nodal force, or applied force along direction 3? Again, from the picture, there is no any applied force. Otherwise, you will see a red arrow, something like this. But no, that means we do not have any applied force along direction 3. 0. Minus P, 0, 0. This is so-called the QK, known force vector. Okay, this is also I call this step 1. Step 1 involves several inspections. You divide structures into element, assign code number, and also find out QK and DK. Normally, you have to think about this in step 1. Step 2, find out K1, K2, and then put them together. These are quite systematic, I think. Not much thing to consider, but involve a lot of calculations for K1, K2 calculations. Right. So we have QK, we have DK. Next, we would like to find out structure sequence matrix. If you know capital K, then you can start to solve the problems. Again, for this problem, K1, K2, element 1, element 2, they have the same length, 2 meters long, 2 meters long. So in terms of the element sequence matrix, all the values inside the element sequence matrix should be the same because they have same length, same E, and same I. So actually, you can reuse this set of number. You can reuse this set of number if because they have the same E, same I, and same length. Only change the code number order. For element 1, for beam, we arrange the member orientation from left to right for beam. So the left end is N, the right end is F. Not N and not F. FN, NF. NY, NY, NZ, and then FY, FZ. Help you to arrange the code number 3412. 3412. This is the code number order. Okay, the code number order help you to assemble the matrices together to form the structure sequence matrix. Structure sequence matrix, capital K. You know the dimension of capital K, right? K is a 6x6 matrix in this problem. Because we have the highest code number is 6. So you can see that K is a 6x6 matrix. The corresponding code number ranges from 1 to 6. You can put it into the big K according to the code number. You can map according to the row number, row index, column index, 1, 1, 1, 2, and so on. Element 2, same, right? Same values, but different code number arrangement. 1, 2, 5, 6. 1, 2, 5, 6. This is I call this step 2. Step 2 calculate the element sequence matrix. And then step 3 may be critical, difficult because you have to combine K1, K2 together to form the whole structure sequence matrix. I highlight the overlapping region in blue color because they overlap only along this row index 1, 2, column index 1, 2. So I highlight this region to help you to see which part you have to do a little bit calculations. How to add that all together? In topic 1, trust analysis, we introduce different skills. You may firstly sort this matrix so that the code number in ascending order, and then enlarge this to a 6x6 matrix. Fill those missing column, missing rows by 0. You may do it in this way, or you may by direct observation, by direct mapping. Say, for example, this element, the row index is 1, column index is 1. You can search in K1 to see if there is any element with the same index, row 1, column 1, row 1, column 1. Then you add them up together. And then the next element, row 1, column 2, which is here and here. One positive, one negative. So when you put them together, it becomes 0. You may do this mapping one by one. There are some shortcuts, right? In topic 1, we mentioned a little bit about the shortcut. You can use the symmetrical property. Because the matrix, no matter element level or structural level, Sylvus matrix symmetrical. They're always symmetrical with respect to this diagonal line. This is the first shortcut you may use. The second shortcut is that this is a big structure Sylvus matrix, but you know some elements are useless, right? Some elements are useless. Say, for example, after observing this for displacement relationship, I think you can tell me that which part is useless in your calculation, right? You can see that displacement along number 4, 5, 6, 0. Dk is 0, simply speaking. If dk is 0, it is a very nice information because it means K12, K22 are useless. Which part is K12, K22? You do a matrix partition. K1, this is K12. This is K22. These two parts always multiplied by 0, dk, in this problem. So actually, column 4, 5, 6, they are not very useful. When you do the example, these two parts are actually useless. You may express them symbolically, like me, K12, K22. It will not affect your final answer. Just pay great attention to the first 3 columns. You'll see more clear when you set up the whole equations. Right? This is the whole for displacement relationship. You can see what I mean before. This region, K12 and K22, multiplied by dk, which is 0. So actually, this part useless. You no need to evaluate their numbers because they will not affect your calculation. Useless. You can express them symbolically using a symbol like K12, K22, or using your own notations. Only need to calculate, only need to evaluate K11 and K21 because this will affect your calculations. This is a force displacement relationship. And then once you have this formula, you have QK, you have DK, you have structure Sylvus matrix, then you can solve our unknown displacement, du. We always start from our unknown displacement, du. I extract the first equation out, QK equal to K11 times du. How to solve this equation? You can solve this equation using many methods. You can use inverse matrix, inverse K11, or you can solve a pre-simultaneous equation, or you may use Gaussian elimination. Depends on which skills you are more familiar with. Solving these 3 equations using matrix inverse or using solving simultaneous equations, your previous skill, math skills. 3 equations, 3 unknowns. This is the full equations. QK equal to K11 du plus K12 dk, but dk is 0. So only K11 du remains. After solving it, you can get our displacement vector d1, d2, d3. Minus 1.66 something, and then p over ei, and then minus 2.66 something, p over ei. Negative and negative, positive, and negative. What are they? It's good to put the answer back to the picture to understand the deformation shapes. We are considering a structures. One end is fixed, the other end is a slider support, At the middle, we have a concentrated force. D1. D1 represents the displacement along direction 1. Negative means downward. It seems makes sense, right? Downward movement because it is under a downward force. D3 is here on the left-hand side of these structures. Based on our understanding, the diffraction, the magnitude should be bigger than D1, right? On the left-hand side. So D3 is a more negative number. That means the magnitude is higher. It also makes sense. Then what about D2? Direction 2. Direction 2 represents the rotational degrees of freedom, which is talking about rotations. From the picture here, our rotation angle is anticlockwise. Anticlockwise means positive, according to our sign conventions in Sylvus method. So the outcome, okay, right, positive numbers, D2, and then D3 on the left-hand side. So you can roughly check your displacement answer by putting them back to the picture. And then based on your structural sense, I believe that you can make some judgment on the directions. Direction may also help you to verify your answer. And then what next? Next, we would like to know the reactions. To find out reactions, you go back to the matrix equation using the bottom part here. Using the bottom part to find out QU. It involves only matrix multiplication. K21 times dk at du, then you can get all the reactions, Q4, Q5, and Q6. You can use matrix multiplications, or you may consider 3 separate equations. Matrix is nothing, right? Just a group of equations, put them systematically to each other. You can always convert them back to 3 different equations. So here, the first row times our displacement vector give you the first element minus 0.5p, and then second row times displacement vector give you the second element, and so on, Q4, Q5, Q6. We have the displacement obtained before on the previous slide. And then you can put them back to the picture. Negative moment. Negative moments mean it is a clockwise moment. Clockwise moment, Q4. And then Q5. Q5 talking about the force at the fixed end. Positive. Positive means upward. Upward force. And then finally, on the here, the last element, Q6. Q6 is negative, minus 1.5p. 6 correspond to the rotation degrees of freedom at the fixed end. Negative means clockwise. Clockwise. So we can convert them back to our reaction diagrams. You know the reactions, Q4, Q5, Q6, and you also know the loadings. You know the loadings. So by using this picture, you can sketch the shear force and moment diagram immediately, right, using this picture. What about shear force diagram? How it look like? At the beginning, we have no any forces at node 1, right? No force. So we believe that we have horizontal zero values in our shear force diagram. And then at the middle, we meet our first concentrated force. So we have a downward jump. And then no force at the middle. No force means the shear force diagram remains horizontal. And then finally, you close the diagrams, and we meet another upward force, and you can see a sudden jump on the top. Moment diagrams. Moment diagram you can also draw using the graphical solutions, graphical method. Depends on the side you would like to use. You can draw moment diagram on compression side or on tension side. We have moment on the left-hand side of these structures. And then what about the chain right here? The first span. graphical method gives us one property. The shear force is equal to the slope in our moment diagrams. Slope. The slope in our moment diagram is equal to the shear force at that point. From the picture, the red line shows you the shear force. Shear force is 0 along the first region, the first span. Where's my cursor? Here. Shear force is 0 along the first span. So the slope in our moment diagram is 0 in the first span. 0 slope means horizontal. Okay. And then we have a negative shear force on the second span. According to this property, when you change this property a little bit, V dx equal to dm, and integrate this equation, it becomes another graphical property. The area of the shear force diagram helps you a little bit about the change in moment. Negative area means the change in moment is negative. So the moment is more and more negative. Then you can draw the moment diagram also in a minute. Something like this. From the reaction diagram, or you may call this force diagram, it is obtained using Sievers method. And then if you know this force diagram, you can immediately draw the shear and moment diagrams using graphical method. And in the textbook, they give you equation to calculate the member end force. Member end force means the force at the end of each member. Here. But as I mentioned in the lectures, there's no need, I think, no need to calculate member end force. If you really need to do so, I suggest you to use equilibrium. Make a cut at your interested sections and then use equilibrium. I think it's much more faster than using matrix. Okay, this is approach 1. Approach 1, we divided the whole structures into 2 elements. So that we have totally 2 elements, 3 nodes, 6 degrees of freedom. Then what about second approach? Approach 2, instead of using 2 elements right here, I would like to use only one single element. Let me change the color. I would like to use only single element in this problem rather than 2. Then what about the structures? It will become like this. If you change the whole structures at one beam element here to here, then you have only 2 nodes, one on the left, one on the right, and you have 4 degrees of freedom. 1, 2, 3, 4. 4 degrees of freedom. Then what about the force? The force P is now acting at the middle between 2 nodes. How to handle this force? In the lectures, we introduced one term called intermediate loading. P is actually becomes intermediate loading if you cut the structures using one element. Okay, how to handle intermediate loading? You can use fixed end force vector Q0. You can convert P to fixed end force vector. So it seems that we can solve the problems using single element, right? Why? What is the target? The target of this problem is to find out diffractions at the slider. Diffraction at the slider. That means we would like to know the diffraction at this point, and also the reactions. The question actually did not ask you to find out the diffraction at the middle. The diffraction at the middle, no need to determine in the questions, right? I just asked you to find out diffraction at the slider. That means here, not at the middle, not at the middle. So there is no need to add a node at the middle, to be honest. So approach one is correct, but it's increased the difficulty of this problem a little bit because you add one extra node at the middle, which make the problem size become bigger. You have more unknown to be solved. Approach two, we don't know what happened at the middle because you just cut the structures. No cut actually. You treat the whole structures as one single element. There's no node at the middle. If there is no node at the middle, then you have no degrees of freedom at the middle. You don't know what happened at the middle. But it seems that it's still able to answer the questions because we just want to know what happened at the two ends. We don't need to know what happened at the middle. Then we assign the code number in this manner, 1, 2, and then 3, 4. We just use the textbook suggestions, assign code numbers starting from position with unknown displacement. In these questions, we have only one unknown displacement, right? Why? Because at fixed end, we have no displacement, no rotation at fixed end. And slider has no rotation, but slider allows free translation in the picture. So actually in this problem, we have only one unknown displacement, D1. D2, D3, D4, they are 0. D2, D3, D3 are D2, D3, D4 are 0. Q1 is the applied force, apply along direction 1, but there is no force along direction 1, so also 0. So you can see that in this problem, if you treat this as one single element, you can simplify the problem a lot. Firstly, you have fewer degrees of freedom. Second, you can see that you have only one element. That means small k equal to big K. There is no need to do assembly in this case because we have only one element. All you have to do is just calculate this extra force vector, Q0. But Q0 is quite easy to evaluate because they are all well divided. You can use the fixed end force diagram that I provided in the lecture notes. Consider the scenario for a beam under a fixed end beam under concentric load and midspan. Yeah, this picture. Yeah, concentric load at midspan of a fixed end beam. Then you can convert the values fixed end moment, fixed end force back to a vector form. Force, moment, force, moment. Ny and Z. Fy. Fz. What are they? Ny means the node n. Y directions, which means shear, right? And then Nz means the moment. Shear moment, shear moment. We follow this notation in member level, and we follow this arrangement in member level. Ny, Nz, Fy, Fz. And then the last term. The last term here is negative because the moment, the fixed end moment on the right hand side is equal to a clockwise direction. Clockwise means negative according to our sign conventions. That's why when you construct this fixed end force vector, we always need to be careful about the sign. The last element is negative according to our notations. So this is how you construct the fixed end force vector for this problem. You convert the force, the intermediate force, to fixed end force and fixed end moment on the two nodes. At the same time, you can calculate the element sequence matrix following our traditional procedures. But this time, the length is equal to 4 meters. The length, because we just treat this as one single element. So the element length become 2 plus 2, 4. The length is 4 meters long. 4 meters long. So the value is slightly different from the previous approach. Now you know K. This K is equivalent to the structure sequence matrix because you have only one element. You just need to rearrange the code number order so that the code number order in ascending order. Oh, you don't need because automatically ascending order. So there's no need to change the code number order. Put all the things together. QK, your matrix, DK, and then the additional force vector on the right hand side. And then you can do a matrix partitioning, cutting. You have only one unknown displacement. So K1 is a 1 by 1 matrix. 1 by 1 is actually it's not a matrix, it's a scalar, right? So how to find out D1? You just need to solve a very simple equation, one unknowns. Everyone should be able to do it. Then you can find out D1 equal to minus 2.667 P over EI. This answer is exactly the same as what we did in the previous approach 1. Same value. You can check yourself, same value. But the consequence of this method is that for approach 2, you cannot find out the values at the middle because there is no node at the middle. So we have no information at the midspan. But there is no need because I did not ask you to do so. I just asked you to find out the slider displacement, not the middle. Next, find out reactions. Q2, Q3, Q4. It's easy, just this number times displacement plus the fixed end force or fixed end moment. It will give you Q2, Q3, Q4. Quite easy. Then you can determine all the reactions. If you know all the reactions, here, 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 if you know all the reactions, then you can draw the shear force and moment diagrams, just like what we did before. So sometime at the beginning means step 1, discretizations. It's good to think about and have a look to see how to cut the structures. Sometimes some special cutting, just like this approach 2, can greatly simplify the problems. I'm not meaning that approach 1 is not correct. Approach 1 is still correct, but it's increased the difficulty a little bit. You have to solve a 3x3 matrix problem. Okay, approach 1 actually show you the example 1 show you the classical procedures using Zimmer's method, and also discuss a little bit about the idea of cutting. Cut into 1 element, 2 element, it will affect the problem size. Read the question carefully and think carefully to see which method is more applicable. What about the next example? Example 2. Example 2 is more straightforward from a point of view. More straightforward and classical example. Example 2, you are asked to determine the nodal displacements and midspan. You are asked to find out what happened at midspan here and find out the reactions at the fixed ends. Similarly, I may give you some time to think about the problems. 1 minute. Testing. Okay, example 2. In this example, can we just change the whole structures at 1 single element? 1 single element. The answer is no, you cannot do so. You cannot change the whole things into 1 single element in this example. Not possible. 2 reasons. Firstly, in this example, we asked you to find out the node displacement at the middle. So you have no choice. You need to make a node at the middle. So that's why you need at least 2 elements in this example, because you have to evaluate the node displacement at the middle. Then you have to insert a node at this point. And second, this problem, you can see that the elements have different properties. EI on the left, 2EI on the right. For this case, you need to break it into two elements. It makes sense because when you use the element series matrix here, you have no choice. You cannot put two EI into one matrix, right? So this matrix apply only for parametric members, cross sections with, a member with same cross section, same E, same I. Otherwise, you cannot use this matrix. Cut this into two elements, element 1, element 2. Then it becomes a very classical problems. Two very nice supports, fixed n, and we have one concentrated force at the middle. We have one applied moment at the middle. This is the applied moment, 40 kilonewton meter. Applied moment at the midspan. The direction is clockwise. Clockwise means negative. So suppose you will see a negative values, negative moments. Force, the force also negative because it's pointing downward. And from the picture, you can see that the force, this force, 20 kilonewton, and the moment, 40 kilonewton meter, they are applied at the middle node. They are applied exactly at the middle node. So in terms of our terminology, they are so-called nodal force. They should be appeared within QK. You will see 20, 40 inside QK. QK contain nodal force, nodal moment. Okay. Then the UDL, 9 kilonewton meter, is uniformly distributed load. In terms of our classification, they are so-called intermediate loading because they apply between the two nodes. So this value will be located within our fixed end force vector, Q0. So you have to know which information should be arranged to which vectors, which part of our equations. Otherwise, your formulation will be slightly different. Okay. So let us have a look of the solution together. One structure. This time you have to plug it into two elements, element 1, element 2, 3 nodes. Each node will have 2 degrees of freedom, 1 vertical, 1 rotations. And then arrange the code number order. Code number you can assign according to the textbook method. Assign code numbers starting from the arrows with unknown displacement. This time, I think it's relatively easy to identify where we have known displacement or where we have unknown displacement. Because this time we do not have those special support slider. Right here are well-defined support fixed end. At fixed end, we have no displacement, no rotation, no displacement, no rotations. So at the middle, we have unknown displacement, unknown rotation. At the middle is free end. So this one actually you can find out the unknown displacement positions immediately at the middle. The other are 0. You can assign code number at the middle first. 1, 2, and then 3, 4, 5, 6 for the remaining 4 arrows. This one is quite straightforward. Code number diagrams. Step 1. Discretization code number diagrams, and then assign the known properties into the structures. Here I put down the force vector, displacement vector. Within the blank, you find out those known information and put it back to the displacement vector. Then it becomes dk. The picture shows clearly that D1, D2, D1, D2 are unknown. Unknown, we call it DU. D3, D4, D5, D6 are 0. We call that known displacement vector. They are 0. And then at the same time, you can construct the force vector. dk involve code number 3, 4, 5, 6. That means qk should involve the other 2 code numbers, 1, 2. qk and dk. Qk and qu. right? And then fill in the blank Q substitute Q1, Q2 into this vector. Q1, direction 1. Direction 1 stands for these vertical directions. Talking about the force. Diamond force, 20 minus, because the force is pointing downward. Q2, direction 2. Direction 2 talking about the rotations. That means the moment. Is there an applied moment at the middle? Yes. We have applied moment this time at the middle. The magnitude is 40, but the direction is clockwise. Clockwise means negative. Negative. So here you can see that Q1 minus 20, Q2 minus 40, Q3, Q4, Q5, Q6 are unknown reactions. So here you can also use our notations, dk, qk, etc. I think it's more important is to construct the whole displacement and force vector. They form part of our force displacement relationship. So right now we have Q equal to KD plus Q log, right? This is the equation we are going to construct. Now you know Q, part of it, not the whole one. You know part of Q, you know part of the D vector. It seems we're missing K, Sylvester matrix. We're missing Q0. Q0 used to represent the intermediate loading. We have to evaluate separately. So in the following task, we found out K and found out Q0. Element 1. Element 1 is the element on the left-hand side of these structures here. There is no any intermediate loading for element 1. Element 1, the length is 4 meters. The EI value is EI, 12 times 1000 kilonewton meter square. You can use our beam matrix, beam Sylvester matrix, evaluate the matrix carefully using the equations. Simple substitutions. And then arrange the code number 3412 as usual. There is no any intermediate loading, so you can say that Q0 for element 1 is a zero vector. Actually, you can ignore it. Actually, you can ignore Q0 here. But here I just make things clear, put a zero vector. And then we do the same thing for element 2. Be careful, element 2, the EI is 2EI. So you can see that the values inside the matrix are slightly different, 2 times bigger than K1. And then arrange the code number carefully according to the traditional methods. But for element 2 is under uniformly distributed load. So in this case, you have to convert the UDL back to a fixed end force vector using our fixed end force diagrams. I put the fixed end force diagram here at the middle for you as a reference. Force, moment. Okay, and the force is WL over 2, moment WL squared over 12. 18, 12, 18 minus 12. Remember that the moment on the right-hand side is equal to a clockwise moment. Clockwise means negative. For element 2, we have fixed end, we have intermediate force. So we have to construct the fixed end moment, fixed end force vector for element 2. The code number order 1256, equivalent to K2, 1256. We have to rearrange the code number so that they're in ascending order. After here, you can formulate the force displacement relationship. Q equal to KD plus Q0. We know all the items right here. K1, K2, add them up together. It gives us structure Sylvester matrix. Maybe you have to rearrange this element a little bit, or you can do a simple mapping. This one is also easy to map because it's not exactly ascending order, but you can divide this into 4 quarters. And you can see that this involve 1, 2, this involve column 1, 2, row 3, 4, and which means here, column 1, 2, row 3, 4, here. You can cut this into different portions, map it into the structure space matrix. This one is not that difficult because the arrangement is a little bit in symmetric manner, ascending order a little bit. And then construct the fixed and false vector. This is, I call this step 3. Assemble the matrix. Find out the big K. You may also use the shortcut, the skills that are introduced before. The symmetrical properties. Structure matrix is always symmetrical. And also you can identify where is the useful part, where is the useless part, etc. Based on the known force, known displacement vector, you can identify which part is useful, which part is useless. Right. From the displacement here, displacement vector, you can identify which part is useless in the surface matrix. Right. DK involve column number 3, 4, 5, 6, which means column 5, column 3, 4, 5, 6, they always multiplied by 0. So it seems that column 3 to column 6 are useless in the formulations. So you can express them symbolically if you have no time. Maybe it's more clear if you group all the things together in a matrix form. DK is 0. And then column 3, 4, 5, 6 always multiplied by DK. So they are useless. Solve for unknown displacement, and then solve for unknown reactions. This one, we have 2 unknown displacement, D1, D2. 2 equations, 2 unknowns, relatively easy to solve. You can use matrix inverse, or you may solve for 2 simultaneous equations. Here it seems that I'm going to use matrix inverse. I firstly move the force vector to the left-hand side, and then multiply the whole things by inverse matrix. Then you can find out D1 and D2. Try to practice how to solve this kind of equations. At least using the method that you're familiar with, either solving simultaneous equations or using matrix inverse. After that, you can find out the reactions using the second half, bottom of the matrix equations, find out Q3, Q4, Q5, Q6. Remember that there is fixed and false vector on the right-hand side. Right. When you go back to this formulation, there is fixed and false vector on the right-hand side. Don't miss this part, otherwise your answer becomes totally different. They are used to take account of the UDL. Then you can put it on the picture to see the arrangement of the shear force and moment on the 2 ends. Actually, this is the answer of this problem. If you like, you may go one step further to plot the shear force and moment diagram for these structures, although I did not ask you in this problem. But it's good to understand how to draw these kind of diagrams. So in the solution, I also give you the diagram for you as reference. If you have time, you can try to sketch the shear force and moment diagrams yourself based on this picture. The answer normally follow the traditional beam side conventions. That means plot on compression side. If you like, you may flip it upside down. It becomes the one that you're familiar with in structural design modules. This is some reference for you to calculate member end force. Again, not important, not very important. Some discussions, short discussions. Right now, we have discussed quite a lot of examples for truss and beam. we discuss a lot of things right here. Trust and beam analysis. Keep using the textbook suggestions. Start to assign code number from positions with unknown displacements. Right. But what happens if I assign code number arbitrarily from left to right? In fact, you can assign code number from left to right arbitrarily without following the textbook method. If you're familiar with Symbols method, actually you can start to change the code number order. Just like this picture, assign code number from left to right, 1, 2, 3, 4, 5, 6. So the unknown displacement here is appeared at the middle, not at the top. Unknown displacement becomes Q3, Q4 rather than Q1, D1, D2. Okay, it's still able to solve the problems. Just follow the code number diagram in consistent manner in your formulations. Personally, I like this code number diagram much more because it makes me more easy to construct the structured sequence matrix. And then you can take a look of the formulations, and you can see that in the force displacement relationship, the unknown displacement appeared along row 3 and row 4. Then how to solve this problem? It's difficult to identify where is K11, K12 in these expressions. In this case, you don't need to identify where is K11, K12. What you have to do, if you find that unknown displacement appeared along row 4, row 3 and row 4, what you have to do, you just need to pick out the row, the equations that correspond to the row of the unknown displacement. What I mean is that pick out row 3, pick out row 4. Then you will see that this equation involves only D3 and D4, no any other unknowns. Two unknowns, two equations, then you can solve D3, D4. Or if you're good in this kind of matrix method, and actually the highlighted region becomes the one that we call Q1 before. Right. By simple multiplication, this row times this column, you can see that the first two columns and then the last two columns, they are multiplied by 0. Only the middle two elements remains. So actually this is so-called the useful part, or you may call this K1 if you like. When you construct the problems, you can ignore the other useless part. You can ignore column 1, column 2, column 5, column 6 because it will not affect your calculations. Just consider the useful portion, especially the highlighted one in blue color. And then when you take a look at the formulation, you can compare with the previous version. Actually, they're the same. They're the same. Same as our previous versions. So don't need to so worry about the code number arrangement. You can assign arbitrarily. Just follow your definition in consistent manner throughout your whole calculations. The textbook method just for introduction purpose and helpful if you help you to find out the known displacement, known force. But personally, I think this one is more easy to apply. Assign code number along one particular directions. Okay. Just want to remind you two things. We will have a lab. We will have a lab next Wednesday. You may find out some information on Moodle, and then we will have a lab on the coming. We will have a computer workshop, 7,000 workshops on the coming Thursday. We just mentioned after the first break, right, about the lab and the workshop arrangement. So what now? We still have some time. Maybe I give you a short break. After the short break, we may start a little bit about the frame analysis. If you have questions regarding to the previous material, perhaps you may also ask me at this during this short break. The workshop, SAP 2000 workshop, I think you're talking about. The workshop begin at 7 o'clock. Yeah, you're right. You can check your timetable. Remember that it's 7 o'clock p.m. Now, one thing, the workshop is not compulsory. If you has already learned how to use SAP 2000, actually you may not compulsory. If you learn SAP 2000 already, then actually you may skip it if you think it's too simple or too boring. But if you want to learn more, if you want to know how to use SAP 2000, if you've never learned that before, then maybe you can also join the workshop together. We may build a simple model to see how to use SAP 2000 to do analysis, find out the diffraction, find out the moment diagrams, etc. How can join? You may go to the computer room on the next Thursday, room 1011. Yes, actually, I think you can see from your timetable, there is a time slot on the next Thursday evening, and the venue is room 1011 at the 10th floor.咁下星期4個 workshop 喺10樓電腦室嗰度嘅，可能有啲同學已經去過都唔奇嘅。Okay, we still have some time for this class, around 30 minutes. Let us fully utilize all the time in these sections. Before the break, we finished our second tutorial examples. Let you know more about beam analysis. We introduced how to some concept about discretizations. What happens if you cut beam into one element, two elements, and also illustrate how to apply Sylvus method for beam analysis. You can also assign code number arbitrarily without following the suggestions in the notes. I showed you similar thing in tutorial 1. You can assign code number in the other orders. I always encourage students to redo the examples in the notes by changing the member orientation, by changing the code number orders. On one hand, it practices the skill of Sylvus method. On the other hand, it also helps you to understand how to arrange code number. Now, we still have some time. Let us talk about frame analysis. Topic 3. Topic 3. Actually, we keep using Sylvus method, but we extend our problems to not beam, but frame. In topic 3, I will go faster because actually the concepts are the same, no difference. We keep using the same approach, Sylvus method. Topic 3, pin frame. Pin frame means 2D frame. 2D frame analysis using Sylvus method. Well, in these sections, we want to use Sylvus method to analyze the behavior of 2D frames. And you can expect that the procedures actually are the same as what we did for beam, what we did for truss structures, same approach. So in this section, I will go faster because not much new things. I think the new thing is only the Sylvus matrix. The other procedures, formulations are basically same as what we learned in topic 1 and topic 2. This is the content of this PowerPoint, topic 3. We firstly introduce our matrix for frame. And then we have to transform the elements again for frame, because frame can be vertical, can be horizontal, can be inclined members. So we have to do some transformations. But the transformation matrix actually are the same as what we learned in topic 1, truss. So I just copy the transformation matrix in section 2. And then you can combine all matrices together to form a global Sylvus matrix. Global Sylvus matrix means the big K. How to form the K? From small k according to the code number. So actually here is also same as what we discussed before. Finally, apply Sylvus method to analyze plane frame. So you can see that I think the entire whole chapter, the new things appeared in the first section. Frame elements, not totally new. And then the remaining thing just simple applications. Let's have a look how to construct our frame stiffness matrix. Firstly, what is frame? What is frame member? We have learned truss, we have learned beam. What about frame? Truss member only take translation. It can be vertical, it can be horizontal. Beam take vertical and bending. Truss take translation. Beam take shear and bending. Frame, from the picture, you can see the frame take all actions. It take axial force, shear force, and bending effect. So frame is more complicated because you can see that there are 3 arrows at each end. At one end, you have 3 arrows. You have shear force, Q and Y. You have axial force, Q and X prime. You have bending moment, Q and Z on each node. So we have many things. Shear, axial force, moment. And also we have translation. We have rotations at the 2 ends. This is why there are so many symbols. We use QFY to denote shear, right? Direction Y prime. Y prime is our local coordinate system. QFY prime is the shear force along Y prime directions at node F. QFX, the actual force at node F, along direction X prime. In that moment, we use QFZ. Z stands for the axis of moment, Z axis. Two ends, node N and node F. We have the corresponding displacement and rotations, dny, dnx, dnz, etc. Then how to formulate the stiffness matrix? One thing, we take counterclockwise as positive. We take counterclockwise as positive, same as beam elements. So what about the element stiffness matrix? You can see that we have totally we have totally 6 forces and moments for one frame members. So you can expect that the member stiffness matrix dimension will be 6 by 6. 6 by 6 matrix for one frame element, 2 times bigger than beam and truss. Here I show you the frame matrices directly. This is the element stiffness matrix for a frame member in local coordinate system. At the beginning, we consider local coordinate system at the beginning, along X prime and Y prime directions. How to get this matrix? Actually, we just use superpositions. How? Truss plus beam give you frame. Truss takes translation, beam takes shear and bending. So when you superimpose 2 things together, it becomes a frame member. So frame member is the most general 2D members, which can take all the actions for 2D members, okay? But it's more complicated because you can see that one member, you have already a 6 by 6 matrix. Normally, you have more than one frame member in the structures. So you can expect that the structure stiffness matrix becomes a very, very big matrix, much bigger than what you found in truss in beam examples before. But anyway, yeah, you can see that this part here comes from the truss matrix, EA over L. Well, here comes from the beam matrix. If you're familiar with the numbers, right? 12EI, 6EI, they are the beam matrix that we found before. EA over L comes from the truss matrix. So superimpose according to the directions. It becomes our frame member stiffness matrix in local coordinate system. Local system is not easy to apply because if you have different frame member, inclined frame, horizontal frame, vertical frame, you cannot combine the matrices together. They have different orientations. That's why we have so-called transformation in the second sections. Anyway, here is the local equation. Small q means the local force, local member end force, equal to the member matrix time displacement, local displacement. Local system, not easy to apply. So you have to convert them to the global system, just like our truss analysis. You have to transform displacement and force. How? Show you a few steps. You have to use cosine theta x, cosine theta y, just like truss analysis. We call the direction cosine. Refresh our memory, we have 2 kinds of coordinate system, local and global. Local means the system local to the member. The X prime, there is a dot on the top right-hand corner to indicate that it is a local system. X prime always along the member length. X prime axis always along the member length. Y prime is 90 degrees to X prime. They are the local axis. Then what about global? Global is the same coordinate system to all members, global. Horizontal for X, vertical for Y. These are the global and local axes we use in truss analysis. And then how to transform them from local to global or from global to local? We follow the same procedures using superpositions. We use superpositions. How? At each node, we have different possible movement. Say, for example, it may under dnx, dny, or under dnz. we consider each movement separately and then map them back to the corresponding coordinate system. Add up all the scenarios together, it becomes your transformation matrix. We used this skill before in trust analysis. We used this skill already in trust analysis. Say, for example, case one. Case one, we consider a displacement, dnx. This is capital D. Capital D means it is a global displacement at node n along x direction, which means here, dnx. dnx, global displacement along the global x-axis and node n along the x direction, horizontal directions. You can map them back into local coordinate system, x prime and y prime. Then you can find the relationship between local and global coordinate for one direction of movement. Say, for example, I map them back to x prime and y prime axis by doing a projections. They are indicated by the red arrows on the pictures. One is cosine, one is sine, one is cosine theta y, one is cosine theta x. They are the direction cosine. Some positive, some negative. These two equations help you transform from global to local system. And then you just repeat this step several times. Consider all possible movement. Here, case one, we consider dnx. Then you can consider dny, dnz, and then dfx, dfy, dfz. Then it will help you to construct all the transformation equations for the whole systems. Case two, dny. Go up. Transform them back to local x prime and y prime axis using direction cosine. Finally, the last one at node n is case 3, dnz. dnz means the z-axis. Z-axis is the one pointing outwards of the paper, which corresponds to the bending axis. For bending, you can use the right-hand rule to define the bending moment directions. You can see that for a 2D problems, it is a 2D problems. For 2D problems, after this rotation of the coordinate axis, it will not change the z-axis. When you rotate the x-axis, x-coordinate system, there's nothing changed to the z-axis. Right? It's keep here. So the thing is that z-axis, no need to convert. Nothing to convert for z-axis. Z-axis global equal to local. This is special because we consider 2D problems. 2D problems we have only transformation between x, y, not z. This slide shows you what happens if you consider movements at node n. Then you may consider movement at the other node f. We do the same thing again. Then you can construct the whole transformation matrix for displacements. At node f, I showed you the outcome directly. Just repeat the things. I showed you the equation for node f, and then you group all the equations together. It becomes a big transformation matrix. This is the so-called displacement transformation matrix for frame element. Bigger, slightly bigger than the trust transformation matrix. But many zero here. Again, there are some intermediate equations help us to derive our final product. Our final product is what? Our final product is going to convert our element matrix. We would like to convert this element matrix from local to global. It requires us to use transformation matrix. I will let you know how to do it very soon. Here is the way how you can derive the displacement transformation matrix. We do the things for force. For force, you can also use this technique, transform local to global, then it's help you to transform all elements to global systems. For force, we apply actual force here. So for example, we have actual force, small q mean local coordinate, actual force along x prime axis. Suppose you have actual force here along the x prime directions. You can project this force back to the global system, horizontal, vertical. This becomes the force transformation equation if there is actual force, q and x prime. No moment because z-axis, no effect. Similarly, you can apply force along the other directions, q and y prime, and then project this to vertical and horizontal. Finally, moment there is no need to convert because we explained the idea before. Z-axis no change into the element. So this is how we transform things. Consider each case separately and then group them together. Group them together. How to find out lambda x, lambda y? They are the direction cosine. It's quite similar to truss member. You define where is not n, not f, and then use the coordinate and not f minus the coordinate and not n, right? And then divided by the length of the member. This is how we calculate lambda x, lambda y, just like truss member. This is the force transformation matrix. Again, there are some equations help us to derive our final equation. Our final equation is stiffness matrix in global system. How? How to derive our global matrix? Well, start from this equation. Start from our local force displacement relationship. Local force equal to local member matrix times displacement vector. Displacement vector, local displacement vector, can be expressed in terms of global displacement, big D. Big D means global. Through a transformation matrix we derived on the previous sections. So here on the right hand side, we successfully convert local displacement to global. Next, we would like to convert force. How to convert force? We can use the second transformation equations. Global force equal to transformation matrix times local force. And local force equal to K prime TD. So what is the matrix? The matrix in global system is equal to T transpose times K prime times T. Actually, we use this procedure to derive our matrix for truss. I just copied the equation from topic 1 to here. We would like to find the expressions of K. How? Using the previous two transformation matrices, using the member matrix of frame. If you have time, you can play with this matrix multiplication. But I can tell you that it's quite difficult because each of them is a 6x6 matrix. You have to conduct 3 6x6 matrix multiplications, which is not easy. So the textbook gives us the expressions. Global member series matrix, frame member. The global member series matrix for frame element expressed in this equation. Normally, in the quiz and examination, you have to use it to find out the member matrix for frame element. It involves lambda x and lambda y, the direction cosine, 6x6. This one we use this more frequently. This one is general to all 2D frame member. It can be applied to a horizontal frame member. It can be applied to vertical frame member or diagonal frame member. Any. You can use this equation to find out their corresponding series matrix. Okay. Give you one good news. The good news is that in the quiz, an examination, I will only assess you horizontal or vertical frame member. Okay, you can mark them down yourself. In the quiz and examination, because of difficulties, I will only assess you horizontal or vertical frame member. It will help you to simplify the problem a lot. Why? Because for horizontal member, say for example, for horizontal member, what is lambda x? What is lambda y? For horizontal member pointing from left to right, lambda x is equal to 1, lambda y is equal to 0. If 1, 0, you put it back to the equation, you can see that there are many 0 terms. Similarly, for vertical member, lambda x 0, lambda y 1, then you can see many 0 in the element matrix. I hope that this can help you to simplify the problem a little bit. Okay. To make it more convenient, I construct some special matrix for you. So for example, if you want to consider horizontal frame member pointing from left to right, then this becomes the simplified matrix. Right? Lambda x is 1, lambda y is 0. I substitute them back to the previous equation. This one. Then it becomes this formula. For horizontal frame member, use it. This is in global system. So you can add up the matrices together. Don't need to care about the directions. Then what about vertical? For vertical frame members, it can be pointing upward or pointing downward. This page shows you the matrix for a vertical frame member pointing from bottom to top. Be careful about the directions. Okay, remember orientations in purple color. If you want to consider a frame members pointing upward, then this is the matrix you may use. The next line shows you the opposite. If you want to consider frame members pointing downward, then pointing downward, lambda y becomes -1. Then it becomes the matrix you use. So you can use the matrix on page 15, page 16, page 17 during the quiz or examinations. Or in general, you may use the one on page 14, although it's not quite complicated, but general to all scenarios. So what we learned the difference between truss, beam, and frame in these short sections. And then we derived our element matrix for frame, and then we convert that to global coordinate system. These are what we learned up to here. Even the concept is not that difficult for truss analysis, right? Quite similar. I mean, for Sylvus method, it's quite similar. Among truss, beam, frame, if you want to use Sylvus method, you follow the same procedures. Discretize the structures into different elements, assign the node, assign the code number, and then find out the element matrix. Truss, beam, frame, we have different element matrix. Now you know all the things, right? You know truss, you know beam, you know frame. And then construct the matrix equation. Q equal to KD for something. Sometimes you may need to consider temperature effect, fabrication error in truss analysis. For beam, you may have fixed end force, right? Q0. And then solve it. Solve for unknown displacement, solve for unknown reactions. So Sylvus method is very, very systematic. The last part in this chapter is apply Sylvus method for frame analysis. Here I go through roughly about the procedures. And then here, your task, if you want to use Sylvus method to analyze frame, then firstly, you have to cut structures into different elements. Element 1, element 2, element 3, assign the corresponding node, assign degrees of freedom, and then assemble K1, K2, K3 to become big K, find out dk and qk, known force, known displacement. Sometimes you may need to consider some additional effect, fixed end force, temperature change, etc. Then, as usual, use the upper part to solve unknown displacement, and then use the second equation, solve unknown reactions. Very, very systematic approach. If I put optional here, if you want to find out the member end force, according to the book, they give you one equations. But as I mentioned many times, I don't think it's necessary to do so. If you want to find out member end force, just make a cut at your interested sections. I think it's much more convenient for hand calculations. But if you want to use computer to do the calculations, then you may need to use matrix approach. Well, I don't think I have time to complete the whole example. So maybe next time we can start from example 1 and then complete this chapter. There are something I want to remind you. Again, the lab and the workshop. I think I remind you many times. The lab and workshop. We have lab and workshop next week. And second, assignment. Assignment 1, right? I showed you last time. Today, you can complete question 1 and question 2. We finished all the things for beam analysis. So at this stage, you can complete also question 2. Try to complete these 2 questions if you have time. The due date of assignment 1 is 14 October. You still have some time, but it's good to start earlier so that you have a more flexible arrangement. One tips for you in question 2. In question 2, you can divide the whole continuous beam into 3 elements: 1, 2, and 3. For the concentrated force on the right hand side, you can treat this as so-called the intermediate loading. Okay. I suggest you to do so because it can decrease the problem size. 3 elements. In the past, some students would like to cut the 3rd element into 2 species, 3, 4. It's okay, but it will increase some additional degrees of freedom, make the problem size become bigger. So I think the most easiest way in this problem is to discretize the whole beam into 1, 2, 3, and then solve it. In the assignment 1, I allow you to use some software. You may use software like Excel, Mathematica, or MATLAB to do the matrix inverse if you are not very familiar with matrix algebra. It's okay if you do so. Okay, just present your answer clearly. Let me know what you are doing, and put down the code number diagram clearly in your solution. Different people, different students may have different code number arrangement. So put down the notation clearly. Example 2 here is quite straightforward. Just a beam under UDL, applied moment, concentrated force. No any special things. This one is quite standard. Similar to the example in the notes. Calculate displacement, calculate reactions, shear, moment diagrams. In all the examples, I show you all the calculations. Question 3. Question 3, we have not yet finished. I just talked about the formulation. Next time, I will show you 2 examples. And then after the next lectures, you will have some idea how to play with frame analysis. So these are the things I want to share with you today. Let's see if you have any questions or difficulties. If no questions, then it becomes the end of this class. Thank you everyone to join this lecture 4. Next time we can finish all the things for Siebert's method, and probably we may start a new topic, structural dynamics. We complete topic 2, right? There is one supplementary example under topic 2. So if you want to practice more about beam analysis, you may go to these supplementary examples, okay? There's one supplementary examples you may download from Moodle. If you have no questions, then this becomes the end of this class. Thank you, everyone.